This is section 4.4, and we're going to be talking about solving equations that contain our higher order polynomials. So equations that have x cubed and x to the fourth and so on. In this section, one of the things we're going to have to contend with is the fact that unlike quadratics, where we kind of always had a fallback, right? We always knew that if all else failed, we could use a quadratic formula. There is no such thing for higher order polynomials. So we're much more dependent on being able to find some other clever method to solve. Okay? Now, in our case, what we're always going to do is we'll always start, kind of like we did with quadratics, by getting the equation equal to 0. So for sure, we're going to start with it equal to 0. So actually, solving the equation will be just like finding the zeros of the polynomial function. Okay? All right, let's think about something for a moment. If I have some sort of higher order polynomial, and if I can factor it with just linear and quadratic factors, then I'm actually home free, because I'll set each factor equal to 0, and certainly we can solve any linear equation equal 0. And as we just mentioned, we can also solve any quadratic equation equal to 0. Maybe we could factor, maybe a square root method, but if nothing else, we always have the quadratic formula. So as long as I can take my equation, get it equal to 0, and then factor into linear and quadratic pieces, I will be able to solve my equation. These first few examples will work like that. All right, so solve the equation over the complex numbers. When I say over the complex numbers, notice that just means both real and imaginary answers. All right, so I have my equation here, and I notice right away it's not yet equal to 0. So let's fix that. I'm going to subtract the 5x and subtract the 5. All right, 4 terms, so I'm looking at grouping here. My first group, I can take out a 3x squared, which makes that x plus 1. And negative between the groups, and then I can factor out a 5. So once again, I'm going to get x plus 1. And that means I can factor this into x plus 1 times 3x squared minus 5. All right, notice what we just did. I have a linear factor and I have a quadratic factor. And I know how to solve those kinds of equations, so I know I'm going to be okay. Either x plus 1 equals 0, or 3x squared minus 5 equals 0. First one's really straightforward. It gives me one of my solutions is x equals negative 1. The second one will take just a little bit more work, but still not too bad. I'm kind of thinking a square root method here. I can get that x squared by itself. 3x squared equals 5. X squared would be 5/3. And if I take the square root of both sides, I get either x's positive square root of 5/3 or x's negative square root of 5/3. And again, I'm fine with you leaving the fractions under the radical, or you could split them up, the square root of 5 over the square root of 3. I'm not requiring that you rationalize denominators. This is just fine. And if you don't even know what that means, don't worry about it. Not required. All right, so I ended up getting 3 solutions. Remember with quadratic equations, we typically got 2 solutions, and this time I got 3. If you look at the degree of my original polynomial, third degree, there's kind of a clue there, and we're going to see this play out over and over. With a degree 3 equation, I ended up with 3 solutions. All right, let's try a couple more. This time I've got a fourth degree equation, so I would kind of expect 4 solutions, but let's see. This is a trinomial. It's already equal to 0, so that part's kind of done for me. And with a trinomial, it is quadratic form. First exponent's double the middle one. So I think I can probably use sum and product. Moreover, I have a leading coefficient of 1, which I really like. So I think I can start by just saying that's 1x squared times 1x squared. And then I'm looking for a sum of 7 and a product of negative 18. So let's see, I think 9 and 2. If we make the 2 negative, that's going to work. Plus 9 minus 2. All right, we've got we've got 2 quadratic factors. In quadratics, I know I can solve. So either x squared plus 9 equals 0, or x squared minus 2 equals 0. Those both look like a square root method would work great. This one would give me x squared equals negative 9. And when I take the square root of both sides, remembering that plus or minus, I'll get x equals plus or minus. I know that negative is going to turn into the imaginary unit, and the square root of 9 is 3, so plus or minus 3i. In the second piece, I would have x squared equals 2. Again, I'm just going to take the square root of both sides, remembering my plus or minus. And that gives me just plus or minus the square root of 2. Doesn't come out evenly, so I'll just leave it like that. Double check. We were expecting 4 solutions because this is degree 4. And notice there's 2 here and 2 here. So indeed, we have our 4 solutions. All right, a couple more. C is already equal to 0, so I'm good with that part. So I'm going to ask myself if I can factor that. Now it's a binomial, and I know that I can factor binomials if it's a difference of squares, which this is not perfect squares, or a sum or difference of cubes. And this one is perfect cubes, right? I could think of it as x cubed plus 3 cubed if I wanted to. Okay. And I'll just remind you what the sum of cubes formula looks like. It says a cubed plus b cubed factors as a plus b times a squared minus ab plus b squared. So just a little reminder there. All right, in this case, the a is going to be the x, and the b would be the 3. So I would start with a plus b, which is x plus 3. And then I get a squared, so that's x squared. Subtract a times b. Multiplying those together is 3x. Plus b squared. 3 squared is 9. So there's my factored form. And once again, linear and quadratic, definitely know how to solve both of those. So I have x plus 3 equals 0. And then I have x squared minus 3x plus 9 equals 0. My first solution is x equals negative 3. Then I have this quadratic. And you may remember we said before that the trinomial piece of the sum and difference of cubes formulas never factor. So you might already know that doesn't factor. Otherwise, it doesn't take too much thinking to realize that sum of -3 and product of 9 is not going to work. So we're going to have to fall back on our quadratic formula this time. X will equal, and again, I'm just going to remind you what that looks like. This one you probably know, but there we go, just in case we need it. Opposite of b would be +3 plus or minus the square root of -3 squared minus 4 times a, which is 1, times c, which is 9, over 2 times 1. So I have 3 plus or minus the square root of, that would be 9 subtract 36. It's -27. Or again, you could put all that stuff under the radical in your calculator if you'd rather do it that way. Over 2. And I'm just going to kind of think my way through this radical here. Definitely we'll have the I because of the negative. And then I've got to see if I could break that square root of 27 down, which I think I can. Perfect square 9 goes into that. 27 is 9 times 3, right? So I could write that as 3 plus or minus. Square root of 9 is 3, so that's 3i. Times the square root of 3. All over 2. And with the imaginary answers, we always split it up into the real part and the imaginary part. So I'd rather write this as 3/2 plus or minus 3i square root 3 over 2. Okay. So I have 2 imaginary answers, one with the plus and one with the minus, and then 1 real answer, for a total of 3 solutions, exactly what I would expect from a 3rd degree equation. All right, I've got one more here. This one I don't yet have in the form I need. It's definitely not equal to 0, and in fact I need to distribute that to get standard form here. So I'm going to start by saying 2x to the 4th plus 6x to the 3rd, and then I'll subtract that 3x squared to get that equal to 0 like I need. All right, I'm looking at this, and this time I have a GCF. So let's factor that out first. I could factor out an x squared. That would give me 2x squared plus 6x minus 3. So x squared equals 0, or 2x squared plus 6x minus 3 equals 0. Here I could just use the square root method. But since the square root of 0 is 0, and positive or negative 0 is still 0, I'm going to get x equals 0. In this quadratic, a sum of 6 and a product of -6 is not going to work. So I think I'm back to a quadratic formula here. Should already be written at the top of your page if you need to peek at it. Minus b would be a -6, plus or minus the square root of 6 squared minus 4 times 2 times -3 over 2 times 2. And let's see, what is that? 6 squared minus 4 times 2 times -3. 60. over 4. I'd like to see if I can break that 60 down in any useful way. I know 4 goes in. I think it's 4 times 15, so that's a possibility. Let's just think to see if there might be anything bigger. 9 definitely doesn't go into 60. I don't think 16 does. No, 25 doesn't. I think that's it. I think 4 and 15 is the best I can do. So I have negative 6 plus or minus square root of 4 is 2 times the square root of 15 over 4. And this time there's no imaginaries, so you don't have to split this up into pieces. But the one thing I probably should do is reduce it. I'm going to notice that all of my coefficients are divisible by 2. So I'm just going to divide this by 2 over 2 to get lowest terms. Negative 3 plus or minus just 1 square root 15 over 2. All right, now we did everything right. Those are the correct answers, but I want to point out to you we didn't actually get the number of solutions that we expected. Remember, this was actually a 4th degree equation, right? It started out with a 4th power, but from what I'm seeing here, I have 2 solutions here, one with a plus and one with a minus, but just 1 solution there. We've talked about this situation briefly before. This 0 is what we call a solution of multiplicity 2. And the reason for that is if you think back to when I had x squared equals 0, I could have written that as x times x equals 0, almost like a factoring in a way. And then I would have had the first x equals 0 and the second x equals 0. So it's almost like the x equals 0 happened twice during the solution process. We call that multiplicity 2. Okay? If we're going to keep in mind that, yes, the degree of the equation predicts the number of solutions we will have, we have to keep multiplicity in mind. I have to count that 0 twice, plus the 2 more solutions over here, to see the full 4 solutions that we would expect. So to answer the question at the top of the next page, did we notice a connection between the degree of the polynomial and the number of solutions or zeros that we found? Yes. The degree is the same as the number of solutions. If we count multiplicity. That statement is actually so important that it's not only a theorem, it's a theorem with a name. A formal mathematical statement that's always true, called a theorem. And this one, like I said, is so important, it's actually called the fundamental theorem of algebra. It says basically what we set up here. A polynomial function of degree n has exactly n zeros, right? N solutions, if you set it equal to 0, counted with multiplicity. As we saw, those zeros could be real numbers. They could be imaginary numbers. Or they could be a mixture of both, some real and some imaginaries. All right, so here's where we are at this point. As long as we're able to factor our polynomial into linear and quadratic factors, we're fine. We can always find the zeros because we know how to solve all linear equations and we know how to solve all quadratic equations. But factoring sometimes is almost a lucky thing, right? There's probably a lot more polynomials that can't be factored than those that can. So here's one more theorem for us, and this can help us sometimes find zeros in the situation where we cannot factor. This is called the rational zeros theorem. And I'll tell you that because that gets a little bit tiresome to write out, I'll usually refer to it as the RZT, rational zeros theorem. It says, if our polynomial function, and this is just that fancy math way of writing a general polynomial function, right? Notice it's degree n and has all those terms on down to the constant term, where all coefficients are integers, so no fraction or decimal coefficients. But if it has a rational zero of the form r equals p over q, then p is a factor of a naught and q is a factor of an. So let's think about that for a minute. A rational number is just a number that can be written as a fraction. So that's why we've written our number here as a fraction. The numerator p is a factor of a naught, or a sub 0, which is the constant term of our polynomial. The denominator, the q, is a factor of a sub n, and notice a sub n is our leading coefficient. So what we're going to be doing is we're going to be considering all the factors of the constant term, could be our numerator, and all the factors of our leading coefficient, could be our denominator. This is going to give me a bunch of possibilities. Not all the possibilities are going to work, because this theorem just says if the rational zero exists, it'll be of that form. So I'm going to come up with a bunch of possibilities, and I'm going to have to check or test my possibilities of this form to see whether one or more of them actually works. So, a couple of notes. First of all, there's no guarantee that a polynomial has any rational zeros. So, rational zeros, this theorem only helps us in cases where there's at least one rational zero. We could try all of them, it could turn out none of them work. We have to accept that. Note 2 is what I was just talking about. The theorem allows us to identify potential rational zeros, p over q, but we're still going to have to test the candidates to see which ones actually work. How do we know if they work? Well, keep in mind, what were we doing? We're finding zeros of the polynomial. Zeros of the polynomial are the numbers that we could plug in, and it should give us 0 for an answer, right? So how are we going to test our possibilities? We'll substitute each one into f of x, and if the value is truly a 0 of the function, the result should be 0. All right. Oh boy, hang on just a second here. I just realized I didn't have Desmos ready and I'm going to need it, but I think I fixed the problem, so I think we can keep on going. All right, so here are a couple of polynomials. We're going to look at one cubic and one quartic polynomial, and our goal is going to be to list all possible rational zeros, and then we'll test them to see which ones actually work, which are truly zeros of our polynomial function. So in our first case here, we have this cubic polynomial, and I'm going to say, what are the possible values of r? P over q. P has to be a factor of the constant term, the -2. Now here's my advice on this. I don't usually worry too much about the positives and negatives until I'm completely done, because all factors could be either positive or negative. So I'm just going to put a plus or minus there. And then the p-values, well, fortunately, there's not that many choices, right? The only factors of 2 are 1 and 2. So I'm going to list my possible factors of 2. All right, the q is a factor of the leading coefficient. Although it's not written here, we know that leading coefficient is really 1. That's even easier. The only factor of 1 is 1. So, what do I get out of this? Well, 1 divided by 1 is 1. So I can either have positive 1 or negative 1. And 2 divided by 1 is 2. So I can either have positive 2 or negative 2. So there are only 4 possible rational zeros for this particular cubic polynomial. Now I'm going to test them. For each value of r, 1, negative 1, 2, and negative 2, I'd like to plug it back into my original function and find f of r. What I'm looking for are the zeros. So I'm looking for ones that actually make that function equal 0. Okay. I'm going to look at 1 or 2 of these by hand, but then we're going to use technology to help us out here. If I plugged 1 back into my original function, I would get 1 cubed plus 1 squared minus 5 times 1 minus 2. 2 minus 2 is 0, negative 5 is what I'm going to get there. And clearly I did not get 0 there. Right? I could do that with each one of these. I could plug negative 1 in, find out what I get, plug 2 in, plug negative 2 in, and see which one actually gives me a 0. Now, plugging that in by hand and doing the arithmetic by hand is kind of a pain. So generally speaking, I will just use a calculator or Desmos to do this. And if I go ahead and want to use Desmos, let me first put in my function. And let's see here. I would like to make a table. And for every x value I give it, I want it to plug it into that function. So I want f of x1. We did 1 by hand and got negative 5. There it is. Desmos does it for us really fast. If we actually plugged in negative 1, it looks like we would get 3. 2 gives me 0, so that's one of the ones I'm interested in. And let's see if there's any others. Does negative 2 work? It does not. I get 4. So, the only one of my possible rational zeros that worked was 2. That means x equals 2 is a 0 of this polynomial f of x. Now I already know it's not all the zeros, right? This is a third degree polynomial, so it should have 3 zeros. I've only got 1 so far. And we'll talk in just a little bit about how this can help me find the others. But I'd like to practice this process one more time. This time I've got a 4th degree polynomial. And I'm going to start again by saying, well, if there's any rational zeros in the form p over q, they could be either plus or minus. And p has to be a factor of the 8. Again, I'm not worrying about the negative because I'm doing the plus or minus at the end. All right, well, there's a few more choices. I could do 1 and 8, or I could do 2 and 4, right? Those are all factors of 8. Q would have to be a factor of 3. Not a lot of choices, but 1 and 3 anyway. So there's going to be a lot more options this time. Actually, first of all, I'll do plus and minus on all of them, but let's start by thinking about all of these. Well, actually, let's do it this way. I could have all of these divided by the 1, so I could have 1 or negative 1, 2 or negative 2, 4 or negative 4, 8 or negative 8. Now I could also do all of these divided by the 3. So 1/3 or negative 1/3, 2/3 negative 2/3, 4/3 negative 4/3, 8/3 negative 8/3. Okay. So a lot of options this time, right? Where there, I don't know, 1, 2, 3, 4, 5, 6, 7, 16 options here. So a lot of things. When this happens, I'm not going to require that you actually show me the whole table like you did here. But what I'm going to do is say, hey, at least do this much. I'm going to actually use Desmos to plug in all of these and see what works, but I'm only going to write down the ones that actually work because it just gets to be a little too unwieldy. So here we go. My new function, my new polynomial, was 3x to the 4th plus x cubed plus 10x squared plus 4x minus 8. And in my table, all of the x values I give it, I want them to plug in and find f of x1. And I'm starting with 1 and negative 1. Oh, negative 1 worked, so I'm going to put negative 1 with an output of 0 in my table here. Trying a few more. It's the next one, 4 and negative 4. And 8 and negative 8, and none of those worked. All right, let's start with the fractions. 1/3, negative 1/3. Oh, there's another one. 2/3 also gave us an output of 0. 4/3, negative 4/3, 8/3, and negative 8/3, and that's it. No more zeros, right? So x equals negative 1 and x equals 2/3 are both zeros of my function. Okay. But again, we know it's not all of the zeros. Since this was a 4th degree polynomial, there must be 2 more. And actually, I didn't write it down, but I had the same conclusion in the first one, right? I only found 1 0 here, and it was a 3rd degree, so I expected 3 zeros. So there must be 2 more. All right, so we've now said, all right, we got this nice little theorem, this rational zeros theorem, and it helps us to find, sometimes at least, some of the zeros of our polynomial. How could I find other zeros? Well, let's see. First of all, if we're solving equations, again, we're finding zeros, so we want to make sure our equation is equal to 0. But as long as it is, suppose we've found at least one rational 0 using that rational zeroth theorem like we were just talking about. Since r is a 0 of our polynomial, what do we know about the factors? Well, if r is a 0, x minus r is a factor, right? We've seen that. We saw that back with the quadratics. If x equaled 5 was a solution, then x minus 5 was a factor. So we now know one of the factors of our polynomial. If that's a factor, I can divide it into the original, and then I have a quotient, which gives me the other factor. Okay? So after I do division, and again, I could do long division, but notice this is the form that works with synthetic. I'll then be able to write my factored form. And once I have the factored form, I can just set each factor equal to 0. And hopefully I'll be down to linear and quadratic and I'll be able to finish solving. So we're going to try this process a couple of times. I'm actually going to build on what we were already working with. In my first example, notice that I've now set my equation equal to 0, but it's the same function from this last example. So we already knew that x equals 2 was one of our zeros. So we already know x equals 2 is one of the zeros. What I'm now going to say is that tells me that x minus 2 is a factor. And if I know a factor, I can divide that factor into the original polynomial, and I should get something with no remainder. So let's try it. I am going to use the shortcut of synthetic division, just because it saves me a little time. I put the opposite of this negative 2 here, so positive 2 in my little box. And then I use my coefficients. 1, 1, negative 5, negative 2. Bringing down the 1, I multiply and add to get 3. Moving over, I multiply and add to get 1. Multiply is 2, and that adds up to 0. Remember, the last number is just a remainder, and when you're doing this process, that remainder should be 0 every time, because we already know we're dividing by a true factor of the polynomial. So what do I get here? 1x squared plus 3x plus 1. So what that means is I can now take my original equation and I can write it in factored form. My factored form would be x minus 2 times x squared plus 3x plus 1 equals 0. So either x minus 2 equals 0 or x squared plus 3x plus 1 equals 0. X equals 2 we already knew, but it kind of comes out of the process. And then here, let's see, a sum of 3 and a product of 1, definitely not factorable. So I'm going to go back to my quadratic formula. Negative 3 plus or minus the square root of 3 squared minus 4 times 1 times 1 over 2 times 1. It's negative 3 plus or minus the square root of 9 subtract 4 would be 5 over 2. It's still a real number, right? There's no imaginary, no negative under the radical, so I don't have to split this up. I can actually leave it just like that since the square root of 5 can't be broken down in any useful way. And there we go. I had a cubic equation, and notice now I have the two solutions here, one with the plus and one with the minus, and then one more here for a total of 3 solutions, just like I expected. Let's try that again. In part B, once again, we kind of have a little bit of a head start. You'll notice that my equation here is just this polynomial set equal to 0. And we had discovered that negative 1 and positive 2/3 were already zeros of the polynomial. So from that rational zeros theorem, we already know x equals, negative 1. And x equals 2/3 are zeros. What I now know is x plus 1 is a factor and x minus 2/3. So they're both going to be factors of that polynomial. So since they're factors, I should be able to divide them out and get no remainder. I'm going to take the easier one first. I'll take the one that's not a fraction. Again, these are both the type that work with synthetic division. They will be because of the way we're setting these up. So here I would change the sign and make that negative 1. And my coefficients are 3, 1, 10, 4, and negative 8. Bring down the 3, and then I multiply to get negative 3. That adds up to negative 2. Multiplying gives me positive 2. That adds up to 12. Multiplying gives me negative 12. Adds up to negative 8. And multiplying gives me positive 8. That adds up to 0, which it should, right? That's my remainder. All right. Now, if I wanted to, well, maybe I will. Let's see, I'm going to work backwards. This is negative 8, positive 12x, negative 2x squared, and that would be 3x cubed, right? I have another factor, x minus 2/3. Rather than go back to the beginning, I'm going to go ahead and divide my new polynomial here by this x minus 2/3. So 2/3 would go in the box. Notice I changed the sign. And my coefficients here are 3, negative 2, 12, negative 8. If you want to take a little shortcut there, notice that I didn't really have to write that out. I could have just grabbed this answer and brought it right back down here, but just wanted you to think about it. All right, bring down the 3 to get us started. 3 times 2/3 is 2. That adds up to 0. 0 times 2/3 is 0. Adds up to 12. And 12 times 2/3 is 8. Adds up to 0. As expected, remainder of 0. This would be 12 plus 0x plus 3x squared, or simply 3x squared plus 12. All right, so I am ready to turn all of this now into a factored form. I have got my original equation. I now know that I can write factors x plus 1 and x minus 2/3. And then after dividing both of those factors out, whoops, that was 3x squared plus 12, sorry about that. I ended up with 3x squared plus 12. So that's a factored form of all of that, which then still has to be equal to 0. Now, technically speaking, if I really wanted to, I could factor a 3 out of here and distribute it there to get rid of the fraction, but it doesn't really matter. I'm going to get the same solutions even if I don't, so there's no real purpose in going through that whole extra step. I'm just going to work from here. So I have x plus 1 equals 0. I have x minus 2/3 equals 0. And I have 3x squared plus 12 equals 0. The two linear pieces just give me the two solutions that I actually already kind of knew, but that's okay. Got to get them again. Here, I'm thinking this time I could probably just go with a square root method. 3x squared would be negative 12. So x squared is negative 4. And if I take the square root on both sides, making sure I get that plus or minus, it's going to be imaginary because of the negative under the radical, and the square root of 4 is 2, so that's just 2i. And notice that fourth degree equation has 1, 2, 3, 4 solutions, just as we would expect. All right, let's do one kind of from start to finish without any heads up. So I have a fourth degree polynomial, and I want to start by finding the rational zeros, and then we'll use them to find all solutions. So we haven't worked with this at all yet. All right, so I'm going to start by applying my rational zeros theorem. P over Q, and P has to be a factor of 20, so unfortunately there's going to be a lot of choices this time. Plus or minus, okay, 1 times 20, 2 times 10, 4 times 5, all factors of 20. At least the Q isn't going to be quite so bad. The only factors of 2 are 1 and 2. So what am I going to get here? I would have, and by the way, when you list, I'm okay with you just putting a plus or minus in front of like a whole big long list, and I'll know it applies to all of them. It gets to be a lot of writing otherwise. So I'd have all of these numbers divided by 1. So 1, 2, 4, 5, 10, and 20. And then I would have all of these numbers divided by 2. So 1 divided by 2, or 1/2. 2 divided by 2 is 1, and that's already in my list. 4 divided by 2 is 2, it's already in my list. 5 divided by 2, I better include that. 10 divided by 2 is 5, I already got that. And 20 divided by 2 is 10, and I already got that. So that's actually the whole list, plus or minus. All right, so we're going to try these in Desmos and see which of these actually make my polynomial equal 0. Again, there's a lot of them, so we'll only write down the successful ones. All right, so our polynomial this time is 2x to the 4th minus 2x cubed minus 3x squared plus 8x minus 20. And I'll make my table, and for each number I give it, I want it to find f of that number. See which ones give me 0. So here we go, 1 and -1. 2 worked. You can't see it, but I am putting 2, 0 in my table. -2 also worked. Nothing else so far. All right, let's try the fractions. 1/2. No more zeros. And then how about the 5/2? Nothing there. So the only 2 zeros I found up here were +2 and -2. And there they are. That means x minus 2 and x minus a -2, or x plus 2, are factors. So we're going to go ahead and do our division. We'll divide out each of these binomials and see what we're left with once they're all divided out. All right, I'm going to start out with the x minus 2. So I change the sign, make that 2. And then I'm going to go back and capture the coefficients of my original polynomial. All right, I bring down that 2 to start me out. And then I multiply to get 4. That adds up to 2. Multiply to get 4, adds up to 1. Multiply to get 2, adds up to 10. And then multiply to get 20, adds up to 0, which again is the remainder, so it almost has to be. Now remember, if you wanted to, you could go ahead and write this out as like 2x cubed plus 2x squared plus x plus 10. But we don't really need to because we have another factor to divide out. So I'm going to do that. Here I've got -2 in my little box. And then it's a continuation of this. So I'm just going to take these values and bring them right up here. 2, 2, 1, and 10. All right, bring down the 2 to get us started. Multiply is -4. Add is -2. Multiply is +4. Adds up to 5. Multiply gives me -10. Adds up to that remainder of 0 as it must. All right, so I now have a result of 2x squared minus 2x plus 5. I have 3 factors, and so I'm going to go ahead and write my equation in its factored form. X minus 2 and x plus 2, we already knew those were factors. And then my quotient here is my last factor. And there is a factored form of this original polynomial that can now be said to be equal 0. All right, we're getting there. So I have x minus 2 equals 0, or x plus 2 equals 0, or 2x squared minus 2x plus 5 equals 0. This gives me the x equals positive 2 and the x equals negative 2 that we actually found with the rational zeros theorem, but they come out of the process. And then I'm not thinking that's going to factor, so let's just go right ahead and put the quadratic formula in here to finish this out. Opposite of b would be positive 2 plus or minus the square root of negative 2 squared minus 4 times 2 times 5 over 2 times 2. What is that? 4 minus 40? Yeah, 4 minus 40 would be negative 36. So it looks like I'm going to get imaginary answers here. That would be 6i. And if I do split this up and write it as real part plus imaginary part, like we're expected to do with imaginary answers, 2/4 reduces to 1/2, plus or minus 6 over 4 reduces to 3/2 I. And so there we go. We got 2 solutions here, 2 more there for a total of 4 solutions. And we found all 4 solutions to our 4th degree equation. All right, we've got a little bit to go yet in this section, but I think this has been a fairly long video, so we're going to go ahead and stop it here, and I'll pick up the last bit in a second video for this section.